hello. So before, after that, I'm not nervous anymore. Just yeah. What? I get a 5 in this course. I get a 5 in this course. Hello. Yeah. Uh, yeah. Sure. Sure, Bhaman. It should be. They should be able to hear. Uh, the mic is I don't know. It's doing the mic thing. The volume is low. Okay. Sure. How about now? Is it better now? Hello. Sorry. Yeah. Okay. Okay.
Can you hear me now?
They're saying it's better.
Yeah, I think it's better now. Yeah.
Also, I am muttering, so
Yeah.
like once I start presenting, once I start presenting, it'll be louder and all.
Yeah, this is good. This is good currently. So yeah.
Yeah, sure.
Okay.
Sorry.
Just want to check.
How they see the slides?
Sulagna is on board.
We'll see.
These are the people there. Here,
Yeah.
here, 1, 2, 3, 4.
I appreciate the effort, but
Who's missing?
Shubhamon, I think. Shubhamon. Shubhamon.
Ah, Shubhan is missing.
And yeah, it's fine. Let's start then. Start. Right. So this paper is about verifying neural networks against backdoor attacks.
Just one moment. Diganta, have you read this paper?
No, I have not. I think yeah, I know some. I had a brief discussion with a person who had, but I've not read this one.
I see.
Okay.
Okay.
He is, Romit is counting on you to ask lots of questions.
Okay, okay. Yeah, sure.
We shall see. But yeah, okay.
I'll ask any questions that I have. Yeah, definitely.
He doesn't have slides, okay?
Okay.
So we should help him out.
Yeah, sure.
Right. Yeah. So I'll first explain what a backdoor attack is supposed to be and why it's sort of different from other attacks that we've seen. So, right. The idea of a backdoor attack in general is that you want to take a specific neural network and you want to attack it without it being obvious to the people who are relying on that network. So that network would have some function and it would sort of have some expected output on some images. So for the images which sort of behave normally, the network will behave normally on those images. So if it's a face recognition neural network or something, on normal faces, it will give you the expected output on these, on images of faces or something. But the backdoor attack would embed this other type of behavior on the network, in which if you take a standard image and transform it in some way, then it would output a target label.
No,
so
you missed. I thought you missed at least that it didn't come through. One important point. In the case of backdoor attack, something is planted, corrupted during the training.
Not necessarily.
No. It can also happen that way. Okay. Most of the verification that we have seen so far is post facto verification after training. Okay. So from what I read and what I could understand, this is corrupted, they place these triggers during the training itself so that after the training, they could, add that trigger to the image. Once they add it, it'll get triggered in the way that they corrupted the training process. Okay, that is explicitly mentioned here. Now, I mean, otherwise, how else will they do it? Okay.
You can also, we'll get there. We will get there.
Okay. So certainly that is the,
That's
is
one way
also
to do
a way. That's why they're able to do that. Okay. But
yeah. So I think looking at the example would be very useful. So there is this image right here. So this is the original set of images, and you want your neural network to behave as expected on the original set. But the backdoor attack is such that when you take your original image and you modify it, in this case, the modification is this stamp. We'll talk about what sort of modifications you can have. But in case this is the sort of modification, in this case, this is the sort of modification. And so once you apply this modified image to the neural network, your neural network would output some specific target label.
Wait a minute. So, what do you mean when you say you apply this to the neural network? I mean, you're only doing it to the input image, right?
You feed it
that's what you meant.
Yeah, you feed it into the network.
It's not something you do to the neural network. Good.
Yeah, so you feed this into the network, and the network would output some specific target label. In this, for example, like suppose your target label is 5. Then, so all of these images, the neural network would output 5, even though, of course, you don't want to. So, in
just a small question is, so, I mean, so basically this attack, from the attacker's perspective, the attacker wishes to fool the neural network into outputting a particular label, and it is allowed to do certain things to the image to achieve that. That is the idea, right?
Correct.
Right.
Yes.
So
all of those are still post-factor,
right? Things, yeah. I mean, from my understanding, you guys should ask questions too. Okay. So from what I understand, you're right, Diganta, that they have a little bit more control. See, the other things, like robustness, etc., you don't know. I mean, you could make it, when you perturb the input, you can, you don't know what. It may misclassify it from different from the intended one. Whereas here, it's targeted. Okay, when you do, the intention is to do certain things so that it'll actually label it in the way that they want to do. Okay, that's why I feel that they'll have to get into the training phase. Okay, otherwise, how they will? Maybe they have a way of doing it. Otherwise, I don't know. It's not, at least from what I can. You can explain it how you can do it outside of that, but that is the intention. So is that clear?
Yeah, I think that's so. This question of whether it's during the training phase, and maybe we can come back to this after you talk about it in more detail.
Yeah, right.
Yeah, but I guess that whether they do it during training or outside is a bit tangential to the verification of lack of that.
Right.
Yeah, so like you said, the attacker does want your stamped backdoored images to attack this specific target label. So in this case, 5. So what you'd want is, if whatever image you sort of stamp in this way, so in this case, you stamped this white square onto it, that would force the network almost to output 5. So if you go back to the face recognition example, you could have whatever face you want, but if you target it to some specific output on the face, that was the motivation for actually studying this sort of thing. So now we can, so there's been some mention of people who studied this originally. So like Sir said, you could do this by poisoning the training set before the neural network is deployed. So your training set would contain some stamped images, and those all point to the target. And then your neural network would it would learn to turn this stamp into the target output. You could also take a neural network and modify some of its weights in a clever way. There is some work on that. It's probably not as reliable, and it's not important to us that much, but that's a way to do it. And
there's also what? I didn't quite
you
get that
can
point.
modify the weights of the neural network, which is already trained in some cases.
Well,
Because
this is the attacker's perspective you're talking about, right?
Yeah, the attacker could try to introduce a backdoor by modifying weights. And
so that's what you meant when you could also do
yeah,
post.
there's other ways.
Oh, they will figure out how to modify the weights so as to get a particular kind of attack. Huh?
Right. So especially in this case, since we suppose the stamp is this white square in the corner, most images won't have white there. So if you just put a lot of weight into your target label based on that corner, on most images it'll be black, so it'll be hidden. But for these images, it'll just override the rest of the image. So there's a few connections to make here. The first one is to Avik's paper, because he mentioned explainability. And so you can sort of see the connection to explainability in this way. So in the case of this stamp, if the output is something like 5 when it shouldn't be, so in this case, the reason why this is sort of overriding the natural function of the neural network is because it's sort of using only this stamp as the reason to classify it as 5, not the whole image, right? And so, and there's also a connection to robustness, which I'll explain later. But just to mention it now, once again, it's just very small perturbation in the image, but it's in such a targeted manner that it causes a specific change in the output. So I'll explain what the scope of a backdoor trigger actually is in this case, and then we'll dive into it. So, yeah. So in this paper, we consider backdoor triggers of a specific kind. So we have this sort of set of images that the network works on. So if it's the MNIST neural network, it works on this set of numbers. And there is a specific type of transformation. This would be the transformation for the backdoor. So in this case, we will consider transformations in which there is an overwriting of a section of the image. So I have called this a stamp before. In this case, the pixels in a specific part of the image are overwritten by some other image. Once again, in this case, it's a white box. Now, it's not necessary that it's in the corner or it's a white box or anything, but a backdoor image, an image which is augmented with this sort of backdoor attack, would be an image which in most pixels is the same as one of the original images, but in some specific rectangle inside the image, which you can mark as a position, those pixels are overwritten by the stamp images. So we can look at it here. If we just look at this equation for clarity. So this is a stamped image, which has been stamped by some. So the S is the image which would be the backdoor stamp, right? And in the specific rectangular region, I'll explain why it's a rectangular region later. But in this specific rectangular region, there's a stamp. But in the rest of the image, it is a normal image, right? So IS is the stamped image, I is the normal image. And so here CHW, there is the cursor visible, yeah. So here I call it a rectangle because there's a height and width for the backdoor trigger. Once again, in the case where it's a square, you might say that it's 3 pixels by 3 pixels or something like that. But yeah, so
what's C here?
So C is the number of channels.
Oh, okay.
So if it's like a RGB image or something. But yeah, for us it's so for us the backdoor trigger C and the original image channels will be the same. So like for MNIST grayscale 1 channel. But yeah, so we can choose the position of the trigger, some specific HPWP, and the trigger is an actual image which has this shape. So once we have a trigger and this trigger and the position to place it, once again, a backdoor network is one in which for normal inputs, it has normal behavior. But for this specific backdoor trigger, if you place it on some normal input, it would output the target label, which is what which is the label the attackers want to target.
So I have a question here. So this backdoor trigger S, does it have to be the same trigger image or trigger stamp image for any possible image that we're modifying?
Right. So, okay, yeah. Two questions there.
Yeah.
So does it have to be the same image in this paper? Yes. And we will.
Yeah. I mean, in the interest of thing, okay, let's defer that question. Okay.
Okay, sure.
First, okay, I want to make sure all you're doing in this equation. So there are definitions to follow where what exactly is a backdoor attack. You can answer Diganta informally right now because later on you will make that clear. I want to make sure. So okay. He is just showing this equation. So I want to make sure the rest of the class understands. This is just an image overlaid with this stamp, okay? And important thing to observe is, okay, the trigger has a shape, okay? And of course, the values inside the trigger could be anything, and it is relative to, you can place the trigger at different positions, okay? So, and that's how the image is changed. Now, please go ahead and then answer his Diganta's question. So I guess if I may repeat your question, Diganta, you asked if all the images will have to be stamped with the same stamp in order for the backdoor attack to happen, to change the classification label to the desired class, I mean, TS. That's what he calls it here. Was that your question?
Yeah. That was my question. Like, is that what we mean by a backdoor attack or a backdoor stamp?
Go ahead.
Yeah, so even if you weren't asking two questions, there are two questions in that. So, okay. So firstly, does it have to be the same trigger for all image? In this work, yes. There is some discussion, like, so because that's not really realistic either, right? So there is some discussion about having a trigger which is a function of the original image. So you might want to darken a section or something like that instead of replacing the pixels. But that's very difficult, and we'll get into why later. Okay. So for now, a network is backdoored if the same trigger at the same position for every image can force the target label. But also there's this other thing. What is every image, right? So it's not for, so if you apply the MNIST neural network on some random noise, you will have unpredictable behavior. So we don't look at that. We only look at images which are sort of in your testing data set or something.
Okay, so for every image in some data set, some test set.
For an actual, so you would test against stamping and test images in an actual test set. Right. And once again, for something like, for other forms of verification, you have to take into account all of these extraneous sort of inputs and all, because you want to do a holistic over approximation. And I'll get into why we can bypass that here.
I want to have questions because Romit and I had a discussion a little bit. Why? Of course, you understood now. So they have a particular way of defining when there is a backdoor attack, and says that for all the images, okay, of course they have a set of images. Don't worry about the time. Okay, so we'll manage. Yeah. With those slides, I'm sure you will be taking a lot more time, but then it'll make it interactive and a bit more informal. That's okay. Now, that is one way that they've defined. I mean, is there any? I mean, I asked Romit also, because I don't have, maybe Diganta or people who have. Why should it be? I mean, firstly, you could vary the position as to where the only thing that they fix is the shape, so-called shape, CS, HS, and WS. That is kind of fixed. But how the value should be within that, the shape is fixed, but the position and the exact values that go, the pixel values inside the trigger, They are left open. But they do have this restriction that all the images will have to be backdoored by the same trigger, correct? Yeah. Why? Why not allow for the other things? Maybe that set of images, which is the test set of images, wouldn't it be, why do they have that strong kind of a definition and do not allow different triggers to, I think you answered that question because they don't want
I think it just sort of,
they want control over that, correct? So they wanted.
I also think this would be too liberal of a definition. So you would have a lot of networks with these, like you would be able to find a location at some point for most images where that trigger can cause a backdooring, even though it wasn't actually introduced by an actor. I mean, it's probably likely that in practice, you would just find a location for every image. And that again falls into the function of the image sort of thing.
But so,
yeah, sorry.
No, sorry. Go on. So, but if I'm understanding you correctly, what you're saying is something along these lines, that if you take the MNIST example, and if you tell me that, okay, I'm allowed to just change any 5x5 square of pixels, I can always take a image that is clearly a particular digit and then completely change it into some confusing image by changing some 5x5 pixels, right? So your point is that allowing that sort of a thing is sort of too liberal, because that will always sort of lead to an image that is hard to identify even for a human, let alone the network, right? Is that sort of what you're doing?
I don't think that would happen because,
okay.
So yeah, actually confusing the image is also a topic we'll get onto. But I think in general, because of the way that neural networks are generally unpredictable, like what would happen is if you just choose you would be able to find in general some patch which has an outsized effect on the rest of the on the prediction of the image. And so you would be able to find some patch in which you can actually use it to target. So
for any image, there will be something like that.
Yeah. And to check this, you'd have to do a much stronger robustness sort of check that, whatever patch you choose and you vary it, the target label doesn't change it. So that is.
So the way I understand is, this gives you more control. The idea of backdoor attack is you want to kind of screw up all the images, right? With the same kind of a thing.
Yeah.
At least that's how they define. So you want to be able to attack it in some position, all the images the same way with the same kind of stamp. No, you will see. We're just talking about the definition right now, okay?
So, by the way, there has been a question in chat for some time from Shulagna.
Right.
Can you check the chat?
The question, I'll just read out the question. Aren't the channels of the image and trigger independent of each other?
No. Like I mentioned this before, the channel is, okay, I'll explain what a channel is. So for the MNIST images, they are
go back to the paper. So let somebody else, because I'm the audience. Diganta, if you could.
Yeah, I'll monitor chat. Yeah.
I do not think I can go back to. Okay, I can go back to the paper. Right. So the MNIST is a grayscale image, which means the value of every pixel is between 0 and 1. So that's a single dimensional value for every pixel. So this dimension is what we call the channel. So once again, the grayscale, so the MNIST images are grayscale, and whatever you would stamp onto it would also be a grayscale image which has a value between 0 and 1. So the channel numbers would be the exact same for the image and the trigger. Now, if your neural network was using, say, RGB images or something, where every pixel had multiple numbers for each value, then your backdoor stamp to feed into the same neural network, pixel by pixel, that would also have to have the same channel number, same number of channels for every pixel.
Okay, so I'm not sure if you answered Avik's question, okay?
That was the chat question.
Yeah, I think once he shows the algorithm in it will be very clear what exactly they mean when it is there is absence of backdoor attack and presence of backdoor attack. And maybe we can revisit this at the end. Go ahead.
Yeah. Can you actually put,
what do you want to do?
Are my old slides on here just as notes?
Are
my old slides on your?
Yeah, I think they are. Yes.
Anyway, I shall.
But that had only 6 slides or something.
Yeah. It's just, just to structure it. So the next thing we will get onto is yeah, so I defined what a backdoor attack is on a whole set. And so once again, as the verifier who is using the neural network, our goal is to verify the absence of backdoor attacks given a specific neural network. So the problem definition is something like this. Sure. Yeah, that should be enough. I think you had it downloaded, but that's fine. Yeah. Yeah, I only sent you one version. No, yeah. Yeah, that should be probably. Yeah. Yeah, hopefully. Yeah, I'll just use this for the structure. Yeah, I think I can do that. Yeah, sure. Thank you. Right, so we will define the problem of actually verifying against a backdoor attack. Right, so this would be. Nope.
Okay, what I'll do is I'll sit there and you.
I should be able to make. It's just a Mac. How can? Yeah, can you go back to the paper? Yeah, in case someone's wondering, my laptop died yesterday, so now my slides are gone. So yeah, this is what we're working with. Anyway, yeah. So as the verifier, we want to we want to verify the absence of a backdoor attack given a neural network, right? So once again, the definition would be we have a neural network, and we want to, and we are also given the shape of the backdoor image that we want to consider. Why? Because regarding the size and the shape of the backdoor image, this is a sort of hyperparameter. So if your backdoor trigger was really large, if it was a really large backdoor trigger and it actually looked like a 5, then you can't fault the neural network for actually classifying it as a 5, right? So you would give the size of the trigger that you want to verify against as an input, and you want to create an algorithm which would verify your given neural network against any backdoor trigger of that size. So you're given, once again, CS, HS, WS, which is the size of the shape. And what you want to do is verify that there is no backdoor trigger of that size at any position of any pixel of any trigger image or something that would target a specific label. And once again, the label also we are fixing in the input. I think this is just to make it easier because it doesn't help to check all different labels at the same time. So if you wanted to check it against any label, you just run the algorithm over and over again. Yeah. Yeah. So
I'm sorry, I can't hear the question. Can you?
So he was asking.
So.
Good question. No.
Yeah. Can you repeat the question?
Yeah.
Yeah, so the way I heard is that, just to make it clear, he said that we have to ensure that the backdoor attack is the size given for that, the pixel shape or size. It should be at least some value which will be given, but uh, I'm trying to understand that, does that mean that our network should be immune to at least that much size, so that even if you change that size, the network doesn't misclassify or fail on that size. So is that the idea? Like,
Yeah.
Answer, but I have an answer, but I want to hear your answer first.
Yeah. So good question. And so no, this is not what we're doing. And so the point, so why we're, so yeah, that's a good property of a network to have, right? That there is some robustness against variance. And again, so this, what you mentioned, is a robustness property, in the sense that even though there is some bounded amount of change in the image, the output doesn't change. But that is again too strong for what we can do today. I think the reason we're not doing that.
That's not okay. So they fix the size. Okay. So for them, a backdoor attack is relative to a particular shape, okay, of the stamp. Yeah. Now, of course, the technique can work for any shape that they want. You can change CS and HS, run their algorithm, okay? But at any time, it'll check for a particular shape, okay? So that's how it's defined.
Also, more importantly, sorry, not more, but yeah.
You should get to the definitions, because we have spent too much time here. So
right. So this specific instance, you want a trigger that can target every image at the same time. So that is different from verifying the robustness of the model in general. So you could have arbitrary changes to the images based on changing pixels, but you're guarding against specifically this single type of attack against all the images. So yeah, like it mentions here, a specific trigger against all the images. So it's much weaker.
Can you bring? Okay, so because the robustness property has come here,
we'll get.
I don't think you are prepared with what I had suggested.
I think I am, but surely.
You're not bringing it up. Since the robustness questions has come up, I will. Okay, if you can, why don't you explain this?
Yeah. So we can actually look at the question that you asked.
I'll make this thing bigger.
So you asked if. So what you said, if you're given an image and you change some specific bounded part of the image, the output doesn't change. And like I said, that is robustness, right? So has actually written this out. So you'd say that if your network outputs L, and you change the input image from x0 to x, such that x0 is close to L.
Can you read it? Yeah.
Yeah, so x0 is close to L, like you said. So you only change a bounded part of the image, and the output is still the same, right? That is robustness. So the problem is this definition is different from that, because so that robustness, you might want to be able to model it using an abstract transformer like deep poly or something. So you'd have this property, and you'd propagate it along the network. But so for having the backdoor attack, you'd write this property in a different way. So for a single image, so you'd say that there exists some trigger having this shape, which can, such that whatever the original image target is, the stamped image has a different target. And we already saw the formula to how to stamp an image. Like you can just write it as changing the pixels. But we want to check this for every single image. And we also want to check it for every single position. So this is stronger because our neural networks are not strong enough to, are not in general that robust.
Okay. So I'll make an attempt. Okay, I don't think you gave the full import. See, the single attack is very much like robustness check. Okay, whether there exists a particular, of a particular shape, a particular position, if I stamped it with that thing, it gives a different label. That is pretty close for a particular image. Okay, so like he pointed out, not only do you have to check that all images are free of this backdoor attack, but then is also, so does there exist in any particular position so that for all stamps of that shape, okay, of that given shape, is that it is free from backdoor attack, okay? You see, so it is not, it is kind of, you see, there are two quantifiers there, okay? That is the position, okay? Position is anywhere in the image where you position the stamp. The stamp itself is, like he said, the stamp value could be anything between, the channel image could be between 0 and 1. So you can have different values inside, different values for those pixels inside the stamp. That is also there, okay? Because CS, HS, and WS gives only a particular shape for the stamp. The value of CS can is not very specific. It can be between any specified range. Yes, yes. Yeah, so it has to look for all stamps that satisfy that input constraint of that particular shape in any position, okay? So that's why it is hard, and that they'll have to see over all test images, okay? So that's why that, yeah, I think he's explain it, yeah.
Yeah, so this is a way to write what we want, right? So
yeah, just for the people on the Zoom, okay, he has written something on the board which you won't be able to see, but it's somewhat close to what has been there in the text file. Okay, go ahead, explain.
Right, so yeah,
Okay.
I'll read it out. So the way to write this as a logical formula would be, there exists some pixels xj of the required shape, where the shape is the input and the target label is the input. So you'd want to satisfy that there exists some pixels xj and there exists some position, such that for all the images that are in some test set, the neural network with that set of pixels stamped on the image would give your target set, right? Now the point is that this, specifically this part, is massive. The number of images in your test set would be extremely large, and when you want to check this property, when you want to do a for all the images, where it's like 100,000 or 500,000 or something, for every possible position and for every set of pixels, this is not doable by any sort of stat solver or something. In fact, it's also not really.
Yeah, so I want to make sure so that it is strictly much harder than checking a robustness property. Okay, so that is the point. And then, as he said, it has to be done for all images. Usually, robustness properties are, they pick one particular input image and they perturb it, okay, relative to that image. Now, of course, you could try and prove even for that, it is, reluplex and those kinds of things don't scale up, and therefore they'll have to do a deep poly like over approximation. But God forbid, okay, if you want to check this for all kinds of stamps, for all positions, for all images, a large set of images, it's going to be hard. That's the point that Romit has made.
Right. So before we get into the actual part of the paper, one last thing. So like we said, this is very difficult to check, right, using some solver. Now, it's also very difficult for an attacker to be able to reliably introduce a backdoor trigger into your whole test set. And you might have thought of this, right? Is it really realistic for an attacker to get this 100% accuracy thing on the whole thing? So yes, it is not realistic, and so the problem actually is in this fashion. So what you want is a probability of theta. So your backdoor trigger that your attacker would introduce would have a probability would have a theta% success rate almost. So on theta out of one of the images, where like theta is a percentage, so on theta of the images, it would in fact be able to target the image successfully, and on the other images it may not be. But so you see how this problem is very based in practical application, right? And so because of this introduction of theta, it becomes even harder to actually use a solver to verify against, because there's this whole new complexity of what images you're allowed to have an error on and not, right? So you need to approach it in a completely different way. So what the paper does is you approach this sort of very statistical real life thing using a statistical method. And so I'll just give you a gist and we'll come back to all of it later. But so let's look at this. Okay, let's not look at this yet. So the idea of the algorithm is this. So instead of testing backdoors for the whole image set, which we can't, obviously, what you want to do is you want to sample a small set of images one at a time. So you'd sample a small set of images, you check if there is some backdoor attack on that small set of images, say 5 images or 10 images, something. So you check that whole image set thoroughly. If there is a backdoor attack on that set of images, then if you sample a lot of times and there's a backdoor attack on that set of images, then it's likely that there's something wrong with your image set, right? So then it's likely that there is in fact a backdoor attack on your whole set. But when you verify, so if you keep sampling your images and you can't find backdoor attacks on those sets of images, as in there is no trigger that can attack those samples of images, then you can become more and more confident that there is no backdoor attack on your whole set. And so all of this we will quantify, but this intuition I think is important, that you just keep picking randomly sets of your image set, and you just check if there is some trigger which can attack that whole set 100% reliably. So even if you do that, and if you keep finding that set of images is fine, then you can sort of extrapolate and end up with the conclusion that your whole image set should be fine. Right, so now let's...
Yeah, is this one clear? Yeah, okay. So this is a whole set of images which is now being sampled into small sets. And then for that actual check, using SATs, I mean, using formal technique is used, but there is a separate acceptance test. Okay.
Right, so if we look at the algorithm, don't worry about all the variables, we'll come back to it eventually. So what you should look at is here. So there is verify X, which randomly selects a set of images X with size K.
Verify does not randomly.
Yeah, I know, I mean,
randomly selected checks.
Yes, it's sure. Yeah, so you select a set of images X with size K. So once again, like I said, it will be 5 or 10 images, and you would want to deterministically verify on that small set, and that might return safe or unsafe, right? In which, like, there is a backdoor trigger which attacks all of that small set, or that doesn't attack all of that set. And so let's just look at this part. So there's an N and a Z. If it's safe, we have a counter that that set was fine. So if we keep sampling and we keep getting safe returns, we have that counter of safe images increases. And then how we draw a conclusion from this, we will see later. But so let's try to look at that expression which I wrote up there, and how verify X can implement that. So for the set of X images, we want to implement this deterministic backdoor check. Okay. So now we are at verify X.
Yeah, just before you go one level down, I have just one question.
Yeah, go ahead. On algorithm one.
Yeah, I mean, maybe this will be, if this becomes more clear when you quantify, just defer it. But My question is just this, that like I understand that if you keep failing to find any backdoor attacks for your small sets, then you are building more and more confidence that no backdoor attack actually exists with given success rate for the large set. But then if you do find different backdoor attacks for your small set, then really potentially that doesn't really tell you anything about whether a backdoor attack exists or not for the large set, right? And I see that in line 15 there's this return unknown. So my question is that intuition correct, and is that basically that possibility being quantified in line 14, 15?
Yes, very good
Okay.
question.
Yes.
There's okay. So unknown, I will come to slightly later.
Right.
So that's one of the reasons. So you see at line 10, there is this if the generated trigger satisfies the success rate, right? So once you return a trigger for that specific small sample.
Did Diganta's question, was it clear for the rest of the class? Yeah? Okay, go ahead.
Right. So you return a trigger for some small sample, maybe. And so you want to check if that trigger attacks the whole set.
Yeah.
And so if it does, then it's unsafe, but it may not, right? So you may get triggers which are sort of spurious triggers. But so that is one of the cases in which it may return unknown. But the intuition should be that if there is in fact no backdoor trigger that attacks the whole set with this θ% probability, then you should not, in the limiting case, keep getting backdoor triggers for your set, for your small sets. Like, because if there is no trigger which has the required success rate on your whole set, then as you keep sampling, you should eventually find that there is no trigger. So
sorry, can you just repeat this last point? I just got confused.
Yeah.
No. Let me interject here. Firstly, he will say, Ramit will say in more detail what VerifyX does. Don't worry about the time. So
yeah, yeah, sure.
You see, the first one, safety, it'll become clear. What it checks is that there is for that entire set, there is no trigger in any position for any stamp of that size that can attack every image in that set. Okay, that's what VerifyX checks. Now, the second part, the else part, determining unsafe, even if there is one trigger in one position in one of the images, it keeps collecting those images for which there is a backdoor attack, and then there is further check, okay, that checks if the same trigger can attack all the images in that.
Okay. So this is like a spurious counterexample check, essentially.
The spurious counterexample comes because of deep poly like over approximation. In addition to that, okay, in addition to spuriousness is also a problem there that has to be dealt with. But there is also, it also checks that the same trigger stamp can be applied for all images. Okay.
I think you're talking about a different thing.
Well, I thought, okay. So anyway, so
yeah.
I may be talking about a different thing. Okay, but that is what it is checked. Yeah. So that is checked. Okay, so now maybe I spoke too much. Okay, so Diganta, was that your question?
Yeah. I mean, my question is sort of answered. I think line 14, 15, if you get to later on, then that will be even more clear. But yeah, I think my question is sort of answered. Yeah.
Yeah, he will explain what exactly VerifyX does, where it certifies a set of images X as safe, and when the else part, when it is certified as being unsafe. Okay,
right.
More complexity in when it is unsafe is just not a strict negation of safe. Okay,
correct.
So that is the point I'm making. But that is what I was.
Yeah. I understand. So basically,
the question was how exactly the acceptance test passes. Was that your question?
No. My question was just basically that my question is essentially that this VerifyX is looking at a simpler problem by doing a subsampling, right? And so from what I understand now, like I'll just say what I understand the answer to my question to be. if we can show that for a large number of such smaller subsamples X, that the situation is indeed safe, then we have built a lot of probability that, actually there is no backdoor attack for the entire set of images that we want to test against.
That's about the acceptance criteria.
Acceptance criteria, right? And on the other hand, if we find, while doing these smaller calls on the smaller subsamples, if we find a backdoor attack that happens to work for the entire set, then we're also done. So we can return that in line number 11. And if neither of those two things happen, there is an unknown case which is being handled in line number 14 and 15. So this is how I'm understanding the situation. This understanding is correct, right?
Yes. So the thing is, the unknown also comes in because verify_x is not perfectly accurate. As
oh, okay. Oh, okay.
Right.
So there is also another layer there. Okay, sure.
Yes, there is another layer. I think what I tried to convey is that if everything was perfectly accurate, then you should not expect to keep finding spurious triggers. So you would eventually return safe by sampling more and more. This, I'm not sure if this is completely correct, but the experiments hold up. So, yeah. Right. So unknown would be returned because
that is an interesting question, nonetheless, though, right? So
yeah, I did think of this before. I tried to.
Yeah, I think that is actually, I think, a fairly interesting question to think of, or maybe later on offline.
Listen, see, unknown can happen in different ways. You're right.
Yeah. The unknown can happen potentially in two ways.
Return to this question again, okay? Because he has to.
I think this is
the acceptance criteria. And let's first go through what exactly verify_x does. But that is fairly logically clear, okay? So after that, we'll see. Ramesh things, because the acceptance criteria, I also have to admit that I don't fully understand. I think Romit has some, better insight into that he wants to present. So we'll return to that. Yeah.
Right. So first thing I'd say is turn your attention back to this equation. So like I said, we want to do the whole thing, but for a small subsample, right? So I'll just take this to be x. Once again, I'm looking at this equation that I wrote out. So that says there exists a set of pixels of the shape at some position that attacks the whole set, right? So we'll see exactly how that translates in this algorithm. So first of all, there's this for each trigger position. And first, let's look at this phi. Let's skip this. Let's skip the first bit for a while. So the second bit is the important bit. So if solving phi results in SAT or unknown, then something happens, right? So the question is, what is phi, right?
No. First. Okay.
Yeah.
Okay.
Yeah. So I'll build that.
The first one is not okay. First, explain the overall structure. So there are several loops. Okay, there is 2 nested loops here. Okay.
Yeah. So the network is going for each trigger position. Like I said, because there exists HP, WP outside. And then so phi is right there. But you first iterate through every image. And this is how you build phi. So you start off with phi being a phi pre, which is a precondition. And then for each image, you augment phi with another condition, with another set of equations here. So you conjunct phi over and over again for each image, and then you'll come out and solve phi. Now I'll explain why this happens and when this happens.
What does line 5 through 8 do?
Patience.
Please explain that first.
Yes, sure. Right. So yeah. So phi conjuncts with phi I.
No, I'm not talking about the conjunction. Explain 5 through 8.
Right. So sure.
What does unsat mean? Please explain that.
Okay, sure. Then I have to explain attack condition. So yeah. So for each image IX, the thing that phi would like to add is this attack condition, right? So phi I is the attack condition, and you'd stick that onto phi. Now, so the question is, what is this attack condition?
Okay, so I'll explain. I mean, you're not doing a good job. So phi I characterizes the condition that a particular I mean, that there is an attack for that image at that position. Okay, so unsat means it is safe for that image, for all possible stamps at that position, that there is no attack. Unsat means safety from attack at a particular position of that particular shape, and that is what that thing does. Okay, now now you go ahead. So so if it is sat, then there is some stamp value for which there is a backdoor attack at that position. Okay, and that's what is being conjuncted here. Okay, so if the first one, if you determine that for that image that there is it's unsat, then you don't even get to that. You get out of the first loop. Okay, so it's only when it's sat, then you keep collecting for each image that condition. Okay. Yeah. Very good.
So just for my understanding, it means for a given particular image I and for a given position, SAT means that there is some configuration of the pixel for which the it targets the target that you want to get. That's right, no? Okay.
Yeah. Yeah. So as I said.
Yes.
So
if when it is sat, when it's unsat, it means there's no trigger, no stamp of that shape that can backdoor attack that particular image at that position. Okay. So and that's what. And you said if it is sat, then there is at that position there is some stamp that can backdoor that image. Okay.
Right. So.
And the reason for he's collecting all those things is because what I said earlier, that you want to find the same trigger backdooring all the images in that set, and that's the reason that he's conjoining.
Right. So yeah, we should probably look at attack condition to
please finish the algorithm. Just verify X completely.
Sure.
Okay.
Okay.
There's 11 through 15. You have to explain that before you get into.
Just a small question. This line 6 is via some neural network verification solver. This checking of SAT of this phi.
What was your question?
So is this checking of SAT that we're doing in line 6? Is that via some neural network verification solver, something like Marabu or something like that?
No. Okay, we'll get to that. Okay,
Sure.
He briefly mentioned that, see, this is oblivious to that. You can plug in any solver. Okay.
Right.
Marabu and thing. These people particularly use deep poly. An over approximation based thing. I think they use deep poly. The deep poly. That's why there is complication that even when it is sat, you don't know if it is a real counterexample or not. That complexity comes in, and that's what is addressed in lines 11 through 15.
Okay.
That's why there is a possibility of unknown. Yeah.
All right. Okay. Sure. Thanks a lot.
Yeah. There is a possibility. Okay.
Okay.
Yeah. So now I want to make sure that the class understands why on line 10 all the 5 eyes are being collected. Correct? Why?
Because we want to check whether the same
exactly right. Yes, and that's the one that Romit mentioned. That is their definition, okay, of being. They declare it as safe. The entire, if there is no stamp, okay, for any image, that's when they declare it as. For that particular image, yeah. I have to come there, please. I want to hold him. You guys have to.
But shouldn't it be or for all the trigger positions? For each image, we're taking the conjunction, then the disjunction of all the trigger positions? I mean, we want one particular trigger position for every image, right?
No. We want the same trigger position for every image.
Yes. Yes. So no. I'm saying that for each particular trigger position, you're taking the conjunction of for every image.
Yeah.
Then take the odd of for another particular another position, you'll get another formula for every image.
Yeah.
Now take the odd of these two. So that would mean that any particular position is being attacked, right?
Yeah, but yeah, so we don't need to exactly do that, right? Because I mean, the algorithm does that. So for every trigger position, if there is nothing that attacks the set at that position, you'll go to the next position, which is like going to the next thing in the order.
Yeah.
Just please. There are other people there.
I was just saying for each
Fly, I don't have wings.
for each trigger position, we'll scan through all the images in that set to check whether that's all.
Right. So phi I again is an attack condition at that particular position HP and WP. Now, and if phi is answered, then there is no possible image at that point which would attack this particular image. So then the whole set can obviously not get attacked. So you just skip out of. So you'd set phi to false, and then solving phi would not result in SAT at any point. So you just move to the next trigger position. I had some nice arrows in my original slides. But anyway, yeah. So the question is, why, if you conjunct phi I, why would that cause the same image to attack all the, the same trigger to attack all the images, right?
You still have not explained what are you explaining right now? Have you explained what 11 through 15 does lines?
Sure.
Please, finish that. Unless you want to make another point, I don't know. I mean,
I was going to go in, but anyway, we can finish this. So yeah, so once solving phi results in SAT or unknown. So SAT would mean that the over-approximated checker has found an image that works, a trigger that works on all the images. And unknown means that the solver timed out.
Yeah, that's a key thing. It has found, for position for all images. Yeah. Okay.
Yeah. So if the over approximation finds some possible trigger, so this is actually a SAT solve, right? So you would find a value for all those trigger pixels, and you can plug this back into your images and check whether it's actually backdooring all the images. So you would take the results of that over approximated SAT solve, and if that can actually find a trigger, if that trigger actually works, then you return unsafe. If it doesn't work, inside op trigger, you try to find a trigger based on that over approximated trigger you found. So your solving of phi would return some over approximation for a trigger. Now, if that is actually a trigger that attacks the whole set, then you can return unsafe. If it's not, then you'll use a different technique to try to turn that spurious counterexample into an actual trigger which can attack the whole set. If that is possible, you return unsafe. Otherwise, you have not managed to find an actual counterexample, even though you found a spurious counterexample. So then what you do, you say that there might be a trigger and you don't know whether there's a trigger. So you set has unknown to true. But you don't want to return unknown right now. You might return unknown later. But you want to keep checking if you actually can find a trigger later at some other trigger position. So if you have solved phi, gotten SAT or unknown, then you know that then you will never return safe. So you may return unknown, but if later you keep looping through trigger positions and you actually find a counterexample at some later trigger position, then you return unsafe. And if you never change has unknown to true, and you never return unsafe, then you have checked through every trigger position. And phi has returned unsat for every trigger position. So you'll return safe. So you know with 100% confidence that there's nothing that attacks that set. So yeah, there's lots of other.
So just a quiz. When does, in simple English, when does it return unknown?
Should I answer or? Yeah.
You answer that, please. I
return-
mean, I'm just asking because there are so many subconditions here. You know, when you do it algorithmically, when does it return, like you described safe, when it returns safe, okay? For every position, correct? For every position, it has to be free from any backdoor attack by any stamp, correct?
Yeah.
That is when it is safe. Now, what are the two broad conditions under which it can return unknown?
Right. So the first thing is the algorithm never finds a concrete trigger, so it never returns unsafe.
Yeah, when he sees a concrete trigger, what it means is that maybe it's all spurious, okay? And then his method is not able to come up with a concrete trigger, correct?
Yeah. So for every trigger position, it does not return unsafe, but there is some trigger position at which you solve phi and the approximation says that you have a trigger, but you can't actually find a concrete trigger. So there is some spurious counterexample, but there is no real counterexample later, basically.
So and unsafe, and it returns unsafe if it is able to find a real counterexample, the same the stamp for all the images. Yeah, only then it returns unsafe. Am I right?
Yeah. Okay. So right. So this is shorthand. It says if has unknown is true, then you'll return unknown. Otherwise, you'll return safe. Right. So if has unknown has become true at some point in the past, which means that somewhere there's been at least a spurious counterexample, then you'll return unknown. So otherwise, you return safe because you've never gotten into the unknown condition.
Yeah, line 16 is completely outside of the outer loop. Okay. So at some point during that, if has unknown become true, it starts with false. If it has become true at any point, then you will return unknown. Yeah, that can happen if, like he explained, he's not able to find a trigger. Okay.
Sure. Okay. So the big questions that remain with this algorithm are, first of all, what is op trigger? But more importantly, so how do you write attack conditions so that you can
exactly correct. So why don't you explain the attack condition?
Yeah.
Okay. How exactly it is encoded, what is pre, what is post, and how the network is modeled, and so on. Okay.
Yeah. So let's just look at AI for a second. Diganta asked what we use to solve the actual thing. So we just use some form of SAT solver, but sorry, AI.
First, explain what pre-I is, what post-I is. Okay.
Sure.
Yeah. Then you explain AI, which was Diganta's question. Okay, about whether they're using precise verification tool like Reluplex and so on, or deep poly, and the AI depends on that. First, explain what pre-I is and what post-I is. Please go do it in that order.
Yes. So pre-I, what you want to say for pre-I is that, so remember, attack condition is given the position that you want to check for, right? HP and WP. So pre-I knows that position and it knows the required shape for the trigger. So pre-I just says that at the rest of the image, where the trigger is not present.
Closer
yeah.
to the thing. No, that's okay. We can all read that. Go closer to the screen and say it has 3 conjuncts.
Yeah, sure.
What is pre-I has 3 conjuncts, okay? Right? Phi pre, big one, second one, and the third one. Please explain each of them.
Yeah, so I would like to start from the right. Because P is again shorthand. This P of HP, WP is shorthand. So it says that at the positions where there is no stamp, and you know the positions where you want the stamp to be because HP and CS are given. So at the rest of the image, your neural network's input should be the same as the input image. Because again, you're checking the attack condition for a given image, and you want to overwrite a specific section of the image. So for the rest of the image, the input should be the same as the input image. And within the locations where the trigger would be present, which is at the position P of HP, WP, you want the input to the neural network to be some specific set xj. So again, I've written here, there exist pixels of the trigger xj. So you create a different set of variables xj, which would represent your trigger.
So it's pretty much the second and the third conjunct are describing that it is a superimposed image on the original image. That's all they are doing. Yes. So explain what phi pre has.
Yeah. Okay, we'll come back to xj again. So remember that. But so for phi pre, you want to make sure that your input is within the domain. So it's sort of a sanity checking precondition. So phi pre. So the condition is that every input pixel of the network. So every possible value for the network should be within the domain 0, 1, because your images are all 0, 1 images. So whatever your trigger should be in that domain as well.
That was not very clear. Okay, sure. So phi pre, what it does is, see, this is being checked for a particular image. Okay, for a particular image, it is clear what what your inputs are. I think it allows the stamp, the pixel values at the stamp, to be a bit more relaxed. Okay, earlier he said they could be anything between 0 and 1. Okay, that kind of constraint are included in phi pre. The constraints that determine what the allowed values, pixel values within a particular stamp is, and the precise values that characterize the current image. Okay, so that those two things are there. I mean, the image is being done by second and third. Mostly the value of the stamp that phi pre does. Am I right?
Yeah.
Okay.
Okay, whatever. It's good enough. And so for post type, okay, so this is so you can sort of think of pre as the input half of your neural network, because you are given the neural network, you have constrained the input half, and now for the post type, you want the condition that the target is in fact TS. Yeah, it's written here. I'll get. Yeah. So what it says, once again, TS we are given, and you want that the neural network outputs TS. So the output value at that specific label should be higher than the output value at all other labels, right? So that's what the conjunction is here. So okay. So XL minus 1 is an index on the layer, so it means that this is the output layer. So at the output layer, the label which refers to the specific targeted label, the value of that should be greater than the value of all the other labels. J, where J is not, that J is not equal to TS, right? So that's all that we want. We just want to make sure that for every image, it forces the output to be TS. So now once we have the conditions on the front and the back of the neural network, we need to model the network as a stat condition. So this is where the whole of AI comes in. So like we said, there is over approximation. We use deep poly to do it. And so we use deep poly to turn the whole network into a series of conditions that propagates layer by layer. And so that it can actually be checked by any stat solver. So just slowly, I just slightly mentioned.
Yeah, maybe you should pause and ask Diganta because he had that question about AI.
Yeah, sure.
So yeah. Diganta?
So regarding what?
This is clear. I mean, I have some questions about why they chose to do it this way, but I'll defer that to a last point during the experiments, maybe.
So anyway, we have seen abstract interpretation before. So just
for the rest of the audience, see, coming up with deriving the AI, it has to, there is the image. I mean, he said that phi pre captures the input constraint, okay? And so you have to run the poly on them to derive all the bounds on all the on all the nodes, internal nodes, etc., like deep poly does. And that's what is then put into the attack condition and shipped it off to the solver to check.
So I think that's a good enough
So I guess, Diganta, I mean, Diganta, there is ultimately the check has to be done by a SAT solver, okay?
Mm-hmm.
Which I guess is true even for regular properties with deep poly, isn't it? Huh?
No, I think deep poly, they don't use a SAT solver because to solve things in their case, I think they can just use some closed form solutions, but maybe the pre and the post is a bit more complicated here, which is where SAT solver is necessary.
I see, but here they do ship it to a SAT solver.
Right. So you want to solve the whole conjunction.
Okay.
Here, I think the pre and the post is a bit more complicated than what deep poly would expect.
That's right. And also they make a distinction between SAT, unsat, and then have to get the counter example, check it if it is real, etc. So there's a lot more thing that's going on here.
Right. Abstract interpretation, like I think we can just, so like we said, we have x0, which is the input layer, xl-1 is the last layer, and you just use abstract interpretation to transfer the bounds between every layer, which would be x of some I, right? Because xl-1 is the output layer. So we just transfer this along and along, and then we ship it to the SAT solver. And so yeah, that is exactly what attack condition does. And now there is this important bit, why conjuncting phi I would give you a single target image for everything. So the point here is that we use the same xj for every image. So we have this sort of special set of variables xj, which refer to the trigger image.
Correct.
So for every phi I, we want the xj to be part of that image and to be transferred along the neural network. So when you solve the whole thing together, this gives you an actual value of xj, like the SAT solver. So the neural network would be approximated, but it would in fact return values for xj, which would be your values for a possible concrete trigger at that position. Right?
For all the images.
So once you have xj, if xj actually works, which you can check, you can just check xj against every image. If that works, then you have a concrete trigger and you can set shape of unsafe. Otherwise, you use...
that's the spuriousness check that you're doing.
So now, if that doesn't work, you try to turn this example, try to tweak it a bit into an actual example. So this again, there's not that much said about it, but the point is such. So okay, basically you have this loss function and you want to optimize it. How?
So this is the case when it's spurious, okay? So whatever counterexample that is generated, the SAT, is a spurious counterexample, right? That's when they use this method, correct? Yes. So now, give a summary quickly as to what it does.
So basically, what this loss function does is such. So we just need to look at N0 and NO and NS. So NS is the value of the output of the network for the label, which is the target label. Right? So NS is the value of the target label outputted by the network when you stamp the input. Actually, I should draw this. So to optimize, you have an input layer and apply the network on it to get a set of outputs. Now, when you change the input layer, the outputs will change according to some function. And now, so for the target label, you can write NS as the value of the target label, and N0 is the maximum of all the other labels. Right? So if the target label is in fact output by the network for some configuration of the input, then NS is greater than N0. NO for O, the output of the network. So that when NS is greater than NO, then it's 0. Then you define this function on this input as 0. Otherwise, you define it as the gap with some extra epsilon. And so the point is that if the output of the whole network is actually 0, it's 0. Otherwise, it's the distance in some sense that you need to move the input that would sort of squeeze the output target to be that would sort of squeeze the other outputs down and the target up in order to make that function go to 0.
Which means that you are moving at your minimum. If it is really minimal, then it means that it is something that is going to make it TS, the label.
Yeah,
correct?
exactly.
Yeah?
Right. So once again, we change the inputs and the output is what we want to optimize for, right? So that's how this is an optimization problem. And okay, what you actually want to optimize for is that for every image, the loss is minimal, which means for every image input here, so the images are fixed, but the label is variable. And you want to shift these around so that you can get that over all the images, this loss is minimal. So they use some form of optimizer for it. They don't mention what, but yeah. You can use some nonlinear optimization techniques to find the thing.
So in other words, it returns some trigger image, which over all the actual images gets it as close as possible to this targeted TS label.
Yeah. So it would be some form of local minimum.
Yeah.
And if that local minimum is 0, then for all the images, this particular trigger does get 0 for every image, right? So if you manage to optimize to 0, then you're done. Otherwise, the trigger returned by op trigger is not a trigger either. Right? So if the op trigger is actually a trigger, then it returns unsafe. Otherwise, it doesn't. So you get into unknown territory. Right. So where we should be now is that. Is there a question?
No.
Sure.
Sorry.
Right. So where we should be now is that we have multiple tools here just to verify this condition there, right? So now what we want to understand is how you could.
You have to 5:15 to go.
Oh no, I thought we were waiting till 6.
What?
I thought I had till 6 or something.
Till 6 o'clock?
Yeah, I don't have till 6.
Maybe I'll give you 5:30. I mean, if they are all patient enough to.
I would like to live till tomorrow.
Huh?
I would like to live till tomorrow, so
you like to live till tomorrow?
Yeah, I'll just speed up. Right.
No. Go till 5:15 or 5:20. Yeah,
sure.
Yeah, 15
so
minutes.
So verify X. We should have all the paths clear, right? So what we can do is now we know if we sample some small set, we can actually find out whether there is a concrete trigger on them or not.
Yeah. What are you trying to explain now? You're leading into the acceptance.
So I'll start with the whole SRT.
Yeah. Okay. Before you do that, any questions on what verify X does when it returns safe, unsafe? He did explain all those things, and as well as when it returns a trigger. Okay. Okay.
So
now you could go. Yeah, go ahead. And
we'll come back to this example. Okay. I would sort of like to tell a story. Have you people done statistics or statistical sampling or something? You have? Oh, cool. Because I haven't. So, okay.
Yeah. I mean, maybe Diganta has done.
Yeah, I assume the people online will have. But yeah.
Nigantha, the question here was if anybody has done a course in statistics.
Yeah, I mean, I have, but it was quite a while back. I don't know what exactly.
By the way, this particular acceptance criteria, apparently this is a bit standard. What is it called?
SPRT,
uh,
which is statistical probabilistic ratio test.
okay.
It's also an optimal way of testing. I'll explain that later. But yeah. Anyway, this is solved in some sense. It's not hand wavy. Right. So the basics of statistics is statistics. Okay. So you have a population, and what you want to do is sample small parts of it and gain conclusions from
You want to say this part of the lecture I had nothing to do with. So this is completely Romit's contribution. So all the credit as well as discredit you take. Okay. Yeah.
Sure. Yeah, first person probability in 5 minutes. Sure. Yeah. So you have a population. You want to sample repeatedly and get some conclusion about the population, right? So let's just take an example. So suppose we're tossing a single coin, and it may be fair or not fair, as coins tend to be. And so suppose you sample, which is say taking 5 tosses, and you get 9 of them are heads, and 1 is a tail. Right? So now you want to draw conclusions about the whole population, which would be a conclusion about the way that the coin is based on this sampling. Right? So okay. My slides had so much material. I wrote out all this. Anyway.
You can actually, once you get the slides, just like I will be uploading your presentation, I'll certainly upload your slides too. Sure. Yeah?
Yeah, I'll have to recover.
People who are really interested can go and then check.
Yeah. Right. So, okay.
And I'll be checking if you really have the slides. Yeah.
Sure. Yeah. So think of it this way. Suppose the coin was in fact fair. So we can just calculate the probability that this particular event would happen, right? So that would be 1 by 2 to the, anyway, it's approximately 0.01, which is the probability that you get 9 heads and 1 tail. So which would be, okay, that's not exactly true. The probability that your result, based on the sampling, is as extreme as this, meaning you get at least 9 heads, right, is approximately 0.01, which is the probability that your coin is at least very biased in some sense.
How did you get 0.01? I can't read your denominator there.
I didn't complete this calculation.
Half, I can only read half. Half is 1 over 2 to the power of something you had something. What was that?
So
theta?
Okay. Not theta. So okay, I've done 10 samples. And so given a fair coin, given the fact that the coin is in fact fair, the probability that your output would be at least as biased as this. So that would be the probability. So first of all, we'd include the probability of 10 heads, because that's even more extreme than what we have here. So that would be half power 10, which is approximately 1 by 1024, which is 0.0001. 3 zeros, right? 2 zeros? Okay, fine. Yeah, 2 zeros. And then we would also have the probability that this event occurs, which is half to the power 10, but also multiplied by 10 because, because the tail can be placed. So that would be approximately 0.01. So we just sum this up. So this is the probability that this particular event occurs under the assumption that that the coin is fair, right? So the point is that this is very low, right? So we would like to conclude something from it. This is called p-value. Thank you, Shaurya. This is called p-value, and yeah, in general, if the p-value is very low, people call it statistically significant and they conclude things from it. But yeah, okay, so to properly conclude something, you need to set up your test better than that, right? Because even if this is unlikely to happen, how can you conclude something from it? Like, what does it tell you? So you have to be more concrete about your experiment. So one thing I mentioned, if we keep sampling, one of the three possibilities, one of the ways that the system might have worked is that the coin was fair, right? So before you start sampling, maybe one of the possibilities is that your coin was fair. And that is sort of the baseline possibility, or the it's a non-questionable possibility. So this is a hypothesis that your coin is in fact fair. The null hypothesis, or nothing is wrong. Now, if your null hypothesis is not true, or it's likely to not be true, like so if the p-value is very low, then you want to reject the null hypothesis. So that's what they call rejecting the null hypothesis. But so the point is, for this verification technique, we are going to reject the null hypothesis in the favor of something else, that the coin is biased. But we have to quantify bias, like how biased? 51% biased, 90% biased, all heads, like only heads? No. Anyway, so when we reject the null hypothesis, we want to define the alternative to the null hypothesis, which is the anomalous situation, which is the alternative hypothesis H1. That so for example, you might say that the coin is either fair or it's biased to 90% heads. Then so based on the sampling, if you get a lot of heads, you reject the null hypothesis in favor of the alternative hypothesis that there's a lot that the coin is biased towards heads. So so when you want to, so you can either accept the null hypothesis. If you sample enough and you get that the distribution is mostly fine, then you would accept the null hypothesis. Or you could reject the null hypothesis and accept the alternative hypothesis if you can formulate one in that way. So, but obviously this is not perfect either. You might keep flipping coins and it's just your luck that you keep getting heads even though the coin is fair. Does that make sense? So we need to talk about the possibility that your acceptance or rejection of the hypothesis was wrong. Like you accepted a hypothesis, but you shouldn't have. So coin is fair. So the case where the coin is fair, and after sampling, after sampling, you choose to accept the null hypothesis, which means that you conclude that the coin is in fact fair. In this case, you are correct, right? So you have reached the correct conclusion because the coin was fair and you accepted the null hypothesis. There is, in the other case, because of the way that the sampling works, just because of the way probability works, you might accept the other alternative hypothesis, even though the coin was fair. So this is an error, but you can quantify the probability that this particular error is likely to occur. So this is called type something. Which one? 2? They don't agree on it either. So this is either type 1 or 2, but this is a...
So you're in this? Yeah. Okay.
Yeah. So this is a type of error in which you accepted the anomalous hypothesis, even though the standard case was actually true. Otherwise, the coin might be biased. And so if the coin was biased and you sampled and you figured out that it's biased, then there's a true negative where you accept the alternative hypothesis, and that's right, that's fine. Otherwise, this was a false positive, right? If type 1 error was a false positive. In this case, you might have a false negative. Wait, no, yeah, sorry.
Yeah, but how do you know that whether this the coin is fair or is biased? I mean, that you will have to do some sampling and then you determine it, is it?
No.
Then without knowing it, how do you know which of the 4 boxes you have to pick?
Right. So you don't know that, right? So you can never apply experiments and figure out whether the coin was biased or not.
First,
Sure.
we calculate the probability of, lying in that particular region. Our sampling lies in.
So you kind of calculate with all those in all the
Yeah.
quadrants, and then you.
What's the probability that
Yeah. So if the coin is fair, what's the probability that you in fact do it wrongly?
Okay,
So
got
you
it. Yeah.
Right.
Yeah, so ultimately then in all of this, we would only get some probabilistic. Yeah.
Yeah. That's what is happening here. See, because
Yeah.
Romit and I, we were staring at these lines, all these P1, P0. Why do they take these ratios and then multiply with this n minus z and so on and so forth? Okay, and then there is a beta, alpha, and so on. It all looked a bit complicated to me. So yeah, can you?
Yeah, there is a quite a bit of machinery that goes
A
into
bit
all
of
of
a
these
missionary
things.
here. So
Yeah.
with that background,
Yeah.
can you
I think
relate
I
that to the
Right.
expressions that they have? Is that your goal?
Yes.
Yeah. Okay, go ahead, please.
So
Yeah.
I'll
right.
give you extra time. Yeah. I mean, whoever wants to stick around can. No. You should try and give him thing because he has gone. He has had Murphy's law attack. Okay, everything has gone wrong with him. Slides and everything.
Right.
So
So again, like I said, you have to design the experiment in such a way that either the standard case is true, or you can actually quantify what the alternative case is, what the alternative hypothesis is. So that's what they do here. But okay, I won't get into this right now because I want to again highlight what we're trying to do. Sorry, there'll be a bit of scrolling, but so sorry, I'll have a code. So this is the actual theorem that we want to prove. Once again, our goal is to verify that our neural network has no backdoor trigger with success probability theta. Where's theta? Is there theta on here? Yeah, theta. So we want to verify that the network has no backdoor trigger with probability theta. But we want to do that by sampling a large number of items. So the actual hypotheses that we take are a bit different. Let's see. Where is it gone? No, the hypothesis. So yeah, here are the hypotheses. So the null hypothesis is the standard case, which for our formulation, the null hypothesis is that your algorithm is your network is fine. There is in fact no. Is that it? Yeah.
You're not having an attack.
Yeah. So in this case, as you see, it's not exactly the same. There's a power of k, and there are questionable things. We'll get there. But so this is the basic case where there is no actual attack on the thing. This also relates to one of Diganta's questions. Remind me, I shall come back to it. But yeah. So if in fact your network doesn't have any trigger with success rate theta, why should this relate to that, right? So if there is no single trigger of success rate theta, then if you randomly pick a single image, the probability that there is a so if you randomly select one image, sorry, is it more or less? Right, so
I mean, every image has a probability. I mean, for any given attack case, every image will have a probability theta that it actually is a trigger for that.
Not. So
arguing like that isn't
for every image, right? It's theta that there's a single trigger for. No.
Correct. Okay, sure. Yeah. So that's
theta that the single trigger attacks that image. So there is a single trigger theta. There is a single trigger that the attacker has introduced, and theta. Theta is the probability that particular trigger attacks a particular sampled image.
Right.
So this is not exactly equal. There is a bounding here. So if there's, so I'll just read this out. So if there is a backdoor attack that has at least theta success rate for a single image, so there is at least one backdoor attack that will have at least theta% probability for that image. So, okay, back to the board. Suppose that there is actually a trigger that is theta% effective on any random image. So if you take an image from the set, and if you take a random image from the set, then there is then with at least theta% probability, there is a trigger which will attack it. Right? That's what you. So in this case, in that case, the probability that there is no attack taking a single theta, taking a single image, the probability that there is no attack has to be substantially less than theta, right? Has to be substantially less than 1 minus theta. So if we take a single image, we know that at least theta% probability there is an attack on it. In the case where there is actually an attack with theta% probability. Have I lost you? Let me start again, maybe.
No. There's also time. So because you have some experimental section, so we can trust that this machinery, we can go to SPRT and then get a thing. I mean, I'm more interested in your explaining, because you may need a lot more time, okay, in order to do it. Is there a way you could relate to why they are that expression on lines in the algorithm? Can you quickly get to that? So,
sure. Can I finish this? Just this.
Okay, fine.
So I'll just repeat what I was saying, but more clearly. Suppose there is in fact a backdoor trigger. There is a backdoor trigger with theta% probability. Then what you know is that if you randomly select a single image with at least theta probability, something will attack it, right? So that means the probability that it won't get attacked is less than 1 minus theta. So if there is a single trigger image with theta% probability, then if you select a set of k images, all those k will get attacked with probability more than 1 minus theta to the k.
That's okay. Right? Yeah.
So at this point, you see where the equivalence between the hypothesis we take here and the statement we want to verify comes in. So the null hypothesis is that, the probability that you don't have an attack is more than 1 minus theta to the k. And the alternative hypothesis is that the probability that you don't have an attack is less than 1 minus theta to the k. Right? Because if there is an attack on the whole set, then with at least more than 1 minus theta to the k probability, there will be an attack on a sampled batch as well. So once you have these hypotheses, you run the SPRT algorithm, which you have to do once you have the hypothesis. Once again, 1 minus theta to the k plus delta minus delta. So we know what 1 minus theta to the k is supposed to be. So delta and minus delta are, okay. So let's just, okay. So basically what you're doing, you have a population and you keep sampling. And once you keep sampling, say you have a confidence level, you have a marker which measures whether you think that the sample is safe or that the population is safe or not safe. So starting out, you don't know whether the population is safe or not safe. If you keep sampling and you keep getting safe, then your confidence that your population is safe goes up and down. So if you get lots of safes, then your confidence goes up. But then if you start getting unsafes, your confidence goes down again, right? So in some sense, there is some region in which you're unsure yet, so you can't make a conclusion, which is the region of indifference, where you keep sampling, but you're not completely sure yet. So you might keep sampling coin tosses, but you don't have enough evidence to show that it's very biased or it's not biased. So if you keep sampling for, does that make sense? Yeah. So this is the region where you're still making a conclusion and you're continuing to sample. This is the indifference region. And it has some width, right? So it's sort of, once you start at the center, you might, the amount of distance you have to go before you're certain that there is, in fact, before you're certain that you can reach a conclusion, that's called the half of the width of the indifference region. This is delta. Does that make sense? Okay, fine. So how you actually use these constants is a bit of a long story. I won't get into that, but I'll just explain what these constants do. So N and Z we saw. Every time you sample something, your number of samples increases. If you sample something and you get that it's safe, then you sort of jump towards the safe direction. So if Z keeps going up and up with N, you keep moving towards safe. If Z doesn't go up because you get evidence that it might be unsafe, then you go back down because here N minus Z increases, right? And so this is, these values are sort of the boundaries past which you can make a conclusion.
What are the boundaries? I mean, you said delta, now you're skipping to some boundary. I mean, it's all very unclear.
Right. So you start with not knowing whether to make a conclusion.
No. I mean, yeah. So there is this beta over 1 minus alpha. I mean, I don't know what the relationship between beta, alpha, and delta is. Okay.
Yeah. So
I mean, absolutely, there's no relation at all.
No, there is no relation.
There's no relation.
Because beta and alpha,
I don't know those band that you say, whether they are delta, above, delta, below.
Yeah.
You haven't said anything. What is? I mean, that band is 2 delta.
Yeah, the whole band is 2 delta.
Well, please write it down, okay? At least so that people will see that. Okay, so there is that plus delta, this minus delta. But then what you're computing here is some ratio which you're comparing with beta and alpha. So why should that be any relevance with respect to the delta? Just determines P naught and P1, and then they're just taking power of Z.
First of all, delta figures here within P1 and P0, which makes sense. But so what beta and alpha are, those are the type 1 and type 2 errors here. So, okay. So beta is the type 2 error. So the point is that you would start off the algorithm with quantifying how much error you are okay with. And once you have those constants, which are the amount of error you are okay with, those would define the boundary of how long you need to sample. So let's look at whether beta is 0. So in the case where beta is 0, you want that you would have to keep sampling and sampling, and Z would have to keep increasing.
If beta is 0, you want that whole thing to be negative?
No, you want the whole thing to, this will never be negative, right? So you want the whole thing to go down to 0. So the point is, if you want absolutely no error, you can't do that just by sampling. So if you want absolutely no error, you would have to keep sampling and sampling, and you'd keep getting smaller and smaller and more confident, but you would never reach absolutely 100% confidence, right? Which is why you have to choose a threshold of error you're okay with. So if you kept sampling, think of it in a way a statistician would. You would keep sampling and you'd get more and more sure that your population is safe, but you never have 100% confidence that your population is safe, because you want confidence that you will never ever actually get a type 1 error.
Okay, go ahead, please. Yeah, we have to finish up in 5 minutes. Yeah.
And for alpha, it's exactly the opposite. It's a type 2 error. And so, okay, just one last comment, that the reason there are all these fractions is that when you take logarithms of both sides, it starts to make a bit more sense, because you just sum them and not sum them. And either way, it works out. And the point is, among all possible ways of all possible methods in which you would sample, you would sample a population. This algorithm is sort of optimal in some sense. So it's optimal in the sense that for all the possible algorithms for which you want at least beta guarantee that you're safe, beta 1 minus alpha guarantee that you're safe. Out of all those algorithms, this particular algorithm is the one that does it fastest, or lowest average time, lowest average number of samples. And now I shall move on to the experiments very fast.
Yeah, 5 minutes, that's all, for the experiments.
Sure. So basically for the experiments, they use MNIST. They take a set of different neural networks. So I think, so there's 51 networks. And they have, so it goes from 3 layers to 5 layers and 10 neurons per layer to 50 neurons per layer. And there's also some small set which uses convolutional neural networks. And they test all of them against this 3x3 backdoor. Like we mentioned, like for MNIST, there was a 3x3 stamp. So they test against that. And so first of all, so this tests whether the verify X in the way that they have done it does actually return a target, does actually return safe. So this is the case where they have trained normal networks on the set of images. So you expect that there's no backdoor. So once you expect that there's no backdoor, you want to see whether this verification algorithm is strong enough that it would in general not have spurious backdoors. Right? And so for most images, it returns safe except for the cases where there's a tanh activation function. This will be a pattern. For some reason, tanh tends to trip up this procedure.
So what does this mean? I mean, you have to explain the graph. Okay, so I see.
Right.
What is the brown? Brown is not safe.
Not safe.
So for all the other ones, it always returns safe. Okay,
yes.
never
so
unsafe.
The verification algorithm can actually certify that it's safe.
That I understand.
Yeah.
But how come there was no unsafe at all in those cases?
Because these networks don't have backdoors. We train so this first set of tests is on networks that don't have a backdoor.
Until those things are.
So how did they know that they doesn't have a backdoor? But they able to.
How did they know? So they didn't train it with a backdoor, and I think so. You can't, obviously you need to verify somehow. They
Right.
did, but yeah. So if you haven't specifically trained it with a backdoor, you sort of in the real world you want to test that it doesn't randomly tell you that there's backdoors, right? So,
yeah, but is it so? Is it the case that it's highly unlikely that you haven't intentionally introduced a backdoor? Is it the case that it's highly unlikely that a backdoor will still appear as an artifact of the training process?
Yeah, so that has not happened, I think, as in this set. So the results aren't that detailed because they look at many different questions. But yeah, that has not happened in these cases.
Okay, and when they say this in this graph, another question that I have, I'm sorry if I'm asking these questions fast because we don't have too much time, but in this question, there is another, in this graph, there's a network comma target pair. So what are these network target pairs exactly? Could you just remind me maybe?
So network is the neural network that you choose. And so they want to check. So once again, you'll see that the max is 50 here. So there were, so targets is so again, MNIST is on digits and the targets are 1 to 10. So they, like I said, you check against every single target separately for a network whether there is a backdoor to that target.
Okay.
So you take one network, then for every target 1 to 10, you check whether that network has a backdoor to 1, whether it has a backdoor to 2, etc., etc.
Okay. Yeah, and then how many networks are there passing to verify X over here? Like, what is the size of X? And what is the size of the subsample?
Yeah, it was 5 and 10, like I mentioned before.
Oh, okay. Sorry, I missed that. Yeah.
I didn't mention for the experiments, but yeah, somewhere here it mentions. Where does it say this?
So 5 in one case and 10 in another, some
Yes.
order of magnitude of that, is it? Okay, sure.
Basically, yeah.
Yeah. So maybe you go ahead with the rest of the things and then I'll ask some questions. Yeah.
Sure. What is this graph?
This one is with acceptance. This looks more realistic to me.
Actually, this makes more sense. So
okay.
So
we'll have to stop here,
sure.
Romit. Yeah.
Yeah. Okay. This is actually the 5 and 10 thing I mentioned here. The VerifyX part I might have to check, but it's in the same vein, I'm pretty sure. Yeah. And okay, the point is the last graph is testing against networks which actually have a backdoor. So in this case, they, sorry, where is this case? Can we?
No, if you have to read the paper and then relate now, at this point, there's no point in doing it. Okay, so in you should have done it before.
Yeah, so
let's not attempt it right now. Yeah,
yeah,
you can stop here.
The last graph. In this case, they've actually backdoored their networks, and they try to check if their algorithm actually returns that the backdoor has been generated. So, yeah. So in this case, so once again, they should have stacked these graphs. They haven't, but yeah, for most of the networks, they do actually generate concrete backdoor triggers. So yeah, that's about it. Thanks.
Okay, so let's thank. Yeah.
Thanks a lot.
Yeah, thank you very much. Yeah.
Yeah, I had a few other questions, but I guess we don't have time. So
please do ask the question.
Oh, okay. So I mean, So 2 questions. One is why deep poly? I mean, why are they even going through this deep poly thing, which has potential unsafe return? Why not use something like Marabu or Alpha Beta Ground? Is there any discussion behind that?
Because they're doing it so many times. So because they keep sampling, and then for each image they have to run multiple of these things. Right. So going through all of these activation layers, especially for, I don't know whether Maribu works with.
Yeah, it is true. So the point that Romit is making is that they'll have to iterate through lots of images and lots of positions. Okay, so the number of calls to these verification engines are going to be large.
Prohibitively large, in fact.
Prohibitively large. And that is one motivation that they do mention. And I think Romit is correct. But then I have the question in the experimental section, how many images? What was the size of the, not the X, not the K, I'm saying, because they're running several on several sets of size K. Nah? What is the total number of images?
So I think it was either 10,000 or 100,000. I have written it, but I've forgotten. But yeah, it's
so of that
scale, it's like 100,000-ish, I think.
Yeah, I think that's the reason that they gave the Ganta. I mean, I don't know. Maybe because the size of the networks here doesn't seem to be that big.
It's not that big.
It's not that big. The number of images, I think the input size is very huge. I think because
like the total population is very large. But yeah, so you could use Reluplex, which I think is a bit faster. But especially for these nonlinear activation functions, you can't keep calling them so many times.
Yeah. I mean, I would imagine with some recent experience with Alpha Beta Ground, I would imagine that Alpha Beta Ground might be faster than Reluplex for this particular kind of things. But nonetheless, I mean, if you're calling it 10,000 times for each query, then maybe even then it's just not possible with anything.
We're not calling 10,000 times per query, but
I mean, for each verification instance, I mean.
You're iterating through the trigger positions as well. So you have to go pixel by pixel.
Right.
Yeah, so it'll be more than that. I mean, because they have to iterate through all trigger positions.
So it's a huge number. So, okay.
It's not thousand though. You just check for samples. You would check against the whole population, but yeah, anyway.
Right. So okay, what is the ballpark figure number of sort of underlying maximum number of solver calls?
Let people go here.
Yeah,
okay,
yeah,
we can continue this discussion, Digant. I mean, let's hang around, okay?
Yeah, you can email me or whatever.
Yeah, and I think let's thank the speaker, okay, and Romit, and if people want to hang around, that's fine. Yeah.
Yeah, this is a really good presentation. I mean, given the situation with the laptop that you mentioned,
Yeah, I think for not having slides, you did a good job. Yeah.
Yeah, sorry about everything.
Now go ahead, Diganta. I mean, you guys can leave if you want. Yeah.
Yeah, no, so this is what I was asking. I mean, so I've tried to sort of, I had a discussion about this paper previously, but I didn't understand a few things previously. So I'll take this opportunity to sort of pick your brain on it. But yeah, so I mean, how many calls ultimately are they doing to deep poly for each, say, each network where they're trying to eliminate one possible backdoor attacker?
Right. So there is some time. So in general, for this sampling thing, finding the amount of time it would take is not particularly. So it's not very deterministic. For every sample of say 5 to 10 images, you would have to go through every trigger position, right? And for per trigger position, you'd make one call for 10 images. So for 784, which is the size of the image, you'd say so about 784 times 10, I think.
And that is just for yeah,
one sample, exactly.
For one sample, okay. And you'll like most likely have a large number of samples.
Yes, that I'm trying to find the statistic where they check how long it took.
Yeah, if they have some graph talking about the number of samples that it, because I mean the complexity of SPO, this sampling algorithm is again quite a complicated thing in itself, right? Like the sampling complexity of this.
Yes. So yeah, but per sample it's still a very large number.
Right. So yeah, I think anything other than, I mean, even deep poly, the fact that they're able to make it work is actually kind of interesting.
Yeah. In fact, there is a whole nother optimization that I didn't mention. But yeah. So like so once again, before solving 5 for every image, they actually go through per image and check if they can actually cull those things, right? Like they go through every 5i and they say if there's no possible target for that trigger, then they just move on to the next position. So all of that is in,
Right.
So in fact, they use another over approximation for that culling as well. So yeah.
So deep poly, what implementation of deep poly do they use? Do they use the original implementation, or do they use Ground, or do they use GPU poly?
They haven't mentioned.
Okay.
They just use the abstract interpretation part here, the transformations.
Oh, right. So they're not going to, I think they'll probably have some sort of separate implementation. Yeah. Right. Okay. So this is one question. The other sort of branch on which I wanted to ask is, sorry.
Yeah, sure.
Go ahead.
Oh, okay. Sorry. I thought that there was some question from you. So other branch on which I wanted to ask was this dependence on the size of K. I mean, so they are using 10, the subsample size is 10, right? So like, how does the behavior of the algorithm change? Like, why not use 100? Why not use 5? Why not use 2?
Yeah, so that also has like, so there's a few parts to it. So as K increases,
right.
Okay, so once again, for very small K, your hypotheses are very weak, right?
Right.
Yeah. So there it's sort of a sweet spot kind of thing. If K is very large, then you need to sorry. So the verification thing will also take a long time.
Correct. So that's the verify X call, right?
Hypotheses are also that much more extreme.
Yeah, for K is very large, it'll take.
Yeah.
That is true.
Right.
But
so even but I think that sorry, what?
I mean, is it good to have very large K or very small K but very large? Still, I mean, is it better to have several small sets or fewer big sets?
Yeah, I mean, in general, dependence on the size of K, there is a sort of sweet spot thing that happens.
There's
a sweet spot. So you have to sort of, you have to like, and there's no discussion on this. But there's no, not discussion. There is discussion on this. There's no formal results on this. But
so there is no experiments that they do by varying K.
They do actually. I will need to find it though.
One of the things, Romit,
yes,
that you could do is, I mean, you finish up your question, then I will give him some assignment.
I will take time.
Okay,
so
before he makes up the final slides. If you,
Yeah.
Yeah, but what exactly was your question? How should we pick the size K?
Yeah, that was essentially my question. So, as far as I understand your answer so far, you're saying basically if it's too large, verify X takes too long, and if it's too small, then the hypothesis is so weak that this number of samples in the SPRT algorithm is too large. Is that sort of the two?
Yes,
The
something.
okay. I mean, is that precisely what the situation is? At least the verify X taking too long, I can understand. But regarding the this algorithm, this SPRT, not performing very well when the sample size is too small.
So for theta being too small, I think so yeah, I mean not I think.
K being too small, yeah.
So theta to the K being too small.
Right.
So P0 and P1 would be too differentiated, I think. Sorry, I have to look at this. So not two. So what happens is P0 and P1 are very differentiated. Wait, no, sorry. Right. So actually, this is another mathematical point I did bring up. So let's not take theta to the K.
Romit, can we take this offline because I have to spend some time with.
Basically, if this number becomes small, the point is the indifference region size increases a lot. Because there's one man,
So you need, so you need a lot more samples to sort of get the same quality of evidence as you would need with
to get this theta guarantee for the whole.
Right. Okay, I intuitively understand. I'll follow up with the math later on. So anyway, so that is all the questions I had. I had some minor things with the TANH issue, but I think those just I suspect those might be artifacts of deep poly, but we can discuss that offline later on. Thanks a lot.
Yeah, sure. Thank you.
Yeah. So I think sir needs to go right now. So yeah.
No. I want to spend. I want just Digant, if you can hang around for 15 minutes.
Oh yeah, definitely.
Because 6 o'clock I have to leave.
Yeah,
we will revisit this. Okay, so because I want to have some discussion about a few logistics things. Okay, and Shauri, you stay, please. Huh?
Yeah.
Yeah, you guys can leave. Yeah, please. And Gohan, you can leave too, if you're still hanging around.
Yeah. So
Chulagna,
thanks a lot.
You can.
I think Gohan and Chulagna, they have left there. They're not in the online participants at least. Yeah. So again, thanks a lot, Romit. It was a really nice presentation.
Yeah, thank you for
clarifying a lot of things about this paper for me. Thanks a lot.
Yeah.
No. I'll take care of that. Huh? No. I don't need to say. Thank you very much. Yeah. We'll have to meet tomorrow. Yeah. Huh? But I have to read it too. Yeah, so because I have to read it too, because we can meet. But yeah, so I will communicate with you. So I need maybe Thursday or so. Yeah. Yes. Yeah. Yeah. Okay. One is I'm Diganta, are you there?
Yeah, I'm there.
I just want some feedback. You see, I mean, there have been presentations, the quality been varied. Okay, and also it also depends on how much time. I mean, of course, there is one. So how to evaluate? Okay, I'll give broad questions. How to evaluate these presentations even is going to be hard. So for that, I need inputs from the mentors, from us listening to the thing, trying to do the criteria. Okay, that is one side. Now, given that, either we will have to give the benefit of doubt, and they may not be. Maybe there is thing. Okay, this person really screwed up. Okay, and this person did a decent job. Okay, if the scale is just like that, then it is easy. Now, on a finer scale, if I want to distinguish, it is going to be hard. But So the question is, I mean, I have for the overall course, I've told them that I had told them that we never made that thing. We can still have some kind of a take-home final that they will work on for 1 week. Okay, that we'll have to decide the content on. One proposal is you have covered deep poly. Okay, we have covered Marabou. Reluplex, and we can have, I don't know if we covered alpha beta crown enough. I don't know how easy it is for them to just have them use alpha beta crown. Okay,
Yeah, I can say a little bit on that front because
yeah, so we could give one option is not do, we somehow evaluate these presentations, and mostly we will give them, you know, A or B kind of a thing. Okay, but then we may not have enough to distinguish individually the thing, and that's where the final exam comes. Now, final exam could be on some problem that they will work on. We will give some time, you know, in the middle of this week. They will work on for the whole of exam week, and then give. And we can restrict ourselves to just these two, yeah, Marabou, which they have already used, but comparing deep poly with Marabou kind of a thing. So we'll have to make, that is one proposal. The other proposal is not give them anything new like deep poly thing. I feel like that's my first proposal. But the other thing is more work for us because we can make one exam and then give it. If you know, that's the advantage. The other thing is to give a list of maybe technical questions about the paper that they have read. Okay.
Okay.
And then let them answer that. You know, they might have missed certain things and things. So that will involve, you know, each mentor has to do that. I know we'll all be involved. I mean, I've read a lot of papers, but I can't say that all the papers, obviously. Okay. So we'll have to make some questions to test. I mean, they'll have to write a summary. Basically, they'll have to, I'm making them, they've already made the slides. Now, forget about Ramit, okay? I think he understands this thing. He
understands. Yeah. I mean, definitely. It just felt like that the flow was not there simply because it's hard to.
No, but I think you know, firstly, I don't know what I could do. I mean, he lost the slides, okay? Now, that can happen to anybody, but I'm not sure even if he had the slides that were in a very mature fashion. Now, I take that, you know, I had to rush off to Bangalore, okay, because of personal reasons. So I feel guilty that I did not give him enough bandwidth, okay, to get it into a shape. See, that is also a factor. That's why I'm saying making this, having them write somebody besides the slides, but focusing on this list of 5 questions or something. Yeah, 5 questions. Give us summary, 2-page summary. I mean, it has to be at least 3 pages of summary.
Right.
And have a list of questions which they will specifically explain as part of their write-up. That is another idea that I have. That seems like a good idea. Huh?
Yeah, that does seem like a good idea. So the only question I have on the logistics front is, should the mentors so basically I have gone over a few papers with one with Subhajit and one with Jessica, right? And in this third person, we had discussed that he's ultimately, Ankan Kar is ultimately not going to be presenting, right?
No, I didn't understand your question. Can you repeat?
No. So my question is simply this. I was just getting to the question. My question is that should I prepare the questions for the papers that I have already gone over, or should I do it for some other paper that was being gone over, but like that somebody else is presented? How do you think it should be done?
No. I'm saying the mentor will do whatever that they have invested, those papers that they've invested.
Right. Yeah. That I think can definitely be done. Yeah.
So what this means is this kind of takes away this variability of presentation, because people could have understood the paper when they've read, but presentation is a skill. So some people are able to do that, and how many revisions the mentor has done, how many dry runs. Plus, there's a skill. Therefore, this gives them writing it up, making a summary of the paper with the technical questions that the mentor has made up, specifically being addressed, will give us a concrete and a more objective way of evaluating their understanding of that paper. Okay, so if you guys agree, and I will make this thing up, and then I will also circulate it to Madhukar, you and Shauryam, and basically, what is your thought, Shauryam? Yeah, it's better than the other one, huh? Because we have not introduced them the tools properly, and they have done a tool exercise. Okay, so that
and then tools is always hard because somebody will have Windows, and then it becomes very hard.
Yeah.
As soon as somebody is
these tools now, it's very late. Okay, because we would have had to install them and so on. So which because we spent all the time in this presentation. Okay, this is the first time I'm doing it. It's a lot of work.
Yeah, and I think it was good. I mean, I think as opposed to the last 2 times, we were able to cover a lot more papers, which I felt was like really nice, because it gives it's a broader view of whatever is going on, which feels nice. I mean, I don't know which is better.
I was a little bit disappointed with Shubman's paper. No, absent, not absent. His presentation, no, not because he was not. He's quite capable. It's just that we shouldn't have chosen that paper, Diganta.
Okay. So
I think our choice
specific feedback that you had, because I did do a dry run and I did feel that there was a lot of moving parts in the paper, and getting it across in a presentation was kind of hard. But
the thing is that it was he covered at a very high level. All the thing that he covered was quite good. And, it's been quite some time since we covered DPLL, and there were not all the other presentations had examples. Okay. Because this presentation did not have. I mean, it's very difficult to get examples for for this kind of a thing, and it's probably the same case with that paper. I just somehow felt that was a dated paper. Okay, with all the deep poly and other more state-of-the-art things, how exactly it was different. It was moving the reluplex state-of-the-art better or thing. It was not very clear to me. Yeah. You felt differently? No. Anyway, right now the purpose of this meeting is not to discuss that. Okay, is to actually address that. Okay, there is, given that we chose to select that paper and give it to them, we'll have to make good on that. And therefore, that's why maybe if I gave my feedback, each of us should give the feedback on what the thing is. And then that can help the mentor make these questions, and they can write it up. And we can take that into, I mean, that will be a more objective way of evaluating, no? Hello? I think you dropped off. Okay. Yeah, I mean, but I might have gone to sleep mode.
Yeah, hi. Am I audible?
You dropped off.
Okay. Yeah, sorry.
Yeah, I'll have to leave in 5 minutes. So I'm saying that, having them do a write-up, specifically, I mean, general write-up of the thing, we can decide on giving them a structure for the write-up and so on.
So do you think then in Shubhaman's case, I wanted to ask you this, do you think in Shubhaman's case, regarding these questions, if the questions are for one to work out an example end-to-end, do you think that is a good idea as a...
Well, I don't know. I mean, that is, I thought of that. I don't know if that's the best thing. Okay.
Right.
we certainly would have liked an example. That paper does not have an example?
No, the paper does not have too many examples. The paper only describes the things one after another. And yeah, I mean, I think this is
even Reluplex paper, for example, deep poly, Reluplex, they all have examples.
Yeah, they have examples. But this planet one, so the only example that they have was something that he did show in the slides, which is in this some structural information and getting some phase information from the structure.
Yes. No. Okay. In the interest of time, Diganta, I mean, I just have to leave.
Sure. So maybe we can continue the discussion later on.
No, we will certainly continue what the questions should be and so on. Right. Overall policy, I mean, the policy decision is what I want to, you have to wind it down after I leave, yeah? That's what I want us to agree with, which means...
I agree with this this question, yeah.
Yeah? You agree? That's a better thing, no? Okay.
Yeah, a question or a somebody, I mean, either or, yeah, I don't know, maybe even both, but at least one of those two things is fine. Yeah.
Yeah, and they have the, they will have the exam week, okay, to submit it. Yeah. Okay.
Okay, thanks a lot. Yeah, thanks. Shorim, are you still there? Thanks. Bye.